some idea of why symmetry is important when we're looking at algorithms operating on abstract, high-level data structures. And we've hinted at the idea that when you generate algorithms from high-level specifications, they have natural symmetries, and those symmetries may sometimes mean that the algorithm is not the most efficient possible. This question sort of was first, in some sense, crystallized in the study of relational databases in database theory, starting in the 1980s, roughly. So, just as a quick reminder, relational database is really a collection of relations, which we think of as tables. So here's a cinema database. This is pick an example from a course I teach on, or taught at least on databases. So in this example, we have three relations. We call them movies, location, and guide. Together they form a cinema database. And each of the relations has three attributes, which we think of as three columns in this table, right? So movies has the attributes title, director, and actor. And then the entries in the table, each one is a tuple with one element for each attribute. Okay. So in a relational database, typically you have a collection of such relations, and you can query it through a query language. Query language might be, for example, built on relational algebra, where the syntax, if you will, each of the individual relations forms a query, and then you have an algebra which allows you to combine these queries into more complex ones. We'll also allow as sort of base atomic relations, not just the relations already in the database, but say singletons consisting of just a single tuple with a single element from your domain. And then we can combine these relations and build up more complex relations as follows. We can select. So select the selection operation. The selection operation selects, now Q is a query and therefore defines a relation. It'll select all those in which the column J takes value A, or maybe select all those in which the columns J and K are equal. Right? So in each case, it selects a collection of tuples from the relation defined by Q. So each expression here defines a relation, which is therefore a collection of tuples. We can project, which is getting from the relation Q a relation of lower rarity by just taking the selection of K columns J1 up through JK. Join, this creates a relation of larger rarity by taking two relations and combining all the attributes. So on the attributes they have in common, as well as others. Take the union of two relations and take the difference. This is the set theoretic difference of two relations. Okay, that defines the relational algebra. The important point to note here is that each expression defines a relation, and a relation is a table. It's a set of tuples, and there is no, for example, inherent order in these things. So the algorithms, when you write down a query and you convert it into an algorithm for constructing the relation, evaluating the query, so constructing the relation that the query defines, the algorithm proceeds entirely independently of how, what order these entries in the database might actually be represented in the physical database. It's working at the level of abstraction of the tables themselves. In the context of database query languages, this has been formalized into a notion of machines like Turing machines, inspired by Turing machines, but which work on abstract structures rather than strings of symbols. So I like to picture this machine like this. So again, you have a, if you will, a finite state control. which has access to a collection of relations. Think of this as the database. It has a number of relational stores, and it can update these stores through operations of join, projection, complementation, or difference, if you will. And in addition, to give it a bit more expressive power, we also allow certain operations of counting, which means you also have numeric registers in which you can put in, for example, the number of tuples which satisfy a certain query. Now, I want to move from databases to looking at logic. There's a clear connection because query languages on relational databases are often modeled in logic. Cord, who introduced the relational algebra, which I just talked about, also introduced the relational calculus, which is really that of first-order logic, and showed that the two are expressively equivalent. And I'm not going to give you the translation, but just use it to introduce first-order logic on first-order predicate logic on it's a collection of relations. So suppose we have some fixed vocabulary of relation symbols. For instance, the three relations we had in our cinema database. And we have some constant symbols which name individual elements which can appear in tuples in the database. And we have a collection of variables. Then the formulas of first-order predicate logic are given by this recursive syntax. We have atomic formulas formed by taking a relation symbol and applying it to a tuple of terms. I'll say a little bit more about that. We have atomic formulas on equality, and then we can combine formulas by the Boolean operations of conjunction, disjunction, negation, and by quantifying existentially or universally. So in these expressions, the x over here and the x over here is a variable, which means an element of this collection. This s and t is either a variable or one of our constants. And this bold-faced t here is a tuple of variables or constants, so a tuple of terms, of length a, where a is the arity of the relation symbol Ri. All right, so essentially the number of columns in its table. So let's ask the question, suppose I give you a first-order sentence in this, so a first-order expression in the formalism I've just defined without any free variables. And ask, what's the computational complexity of this problem? I'm given a structure. What is a structure? So I mean just a finite universe, along with an interpretation for each one of the relation symbols and constant symbols in our vocabulary. And I'm asked to decide the question, is the sentence phi true in the structure A? What can we say about the complexity of this problem? Since I fixed the sentence phi and the input is just a structure, this is another way of saying this is how complex can the collection of finite models of a fixed first-order sentence be? So we're going to talk about the complexity of a class of finite structures. So the objects we're talking about are finite structures. But as I noted before, when we define complexity classes, we talk about complexities defined on things like Turing machines. And the input to a Turing machine is some string of symbols in a fixed alphabet. So we need to fix some way of representing finite structures as strings just to ask the question about complexity. I will give you such a fixed representation. So I'm going to use an alphabet with three symbols, 0, 1, and the hash symbol. And we proceed as follows. Consider structure A. For simplicity, I've left out the constant symbols at the moment. I think it should be an easy exercise to see how you would add these. And say the elements of my structure are A1 through AN, little a1 through AN, and I fix a linear order. So, put them in this order, A1 through AN. Doesn't really matter what order. And once I have an order, then I can represent any relation of arity k as a sequence of zeros and ones of length n to the k, right? So essentially there are n possible elements of A. So n to the k possible tuples. And because I've fixed a linear order, I can order all k tuples, say in lexicographical order. And for each tuple, it's either in the relation or it's not. So that gives me a symbol 0 or a symbol 1. So I write this for the string of zeros and ones that I get. It represents the relation Ri. Note, and I've emphasized by putting the subscript, what particular string I get depends upon what order I fixed. With a different order, I'll get a different string. Okay. So in order to interpret this string as a relation, I have to have fixed this order. Okay. So now I will write out my structure as this particular string of symbols. It starts with n ones, right? So these are just the symbol 1 repeated n times, where n is the number of elements in the structure. So the purpose of this bit is just to sort of say in front what the size of the structure is. That helps us interpret the rest. And then for each one of the relations, I write out its representation and I separate them with these hash symbols. Okay. That's it. So now I've got a string in this 3-letter alphabet which represents my structure. Now, why did I write out this n1s? Well, I do need to say what the size of the structure is. Of course, I could have done it in binary. That just creates a slight problem where in the special case where I have no relations whatsoever, the length of the string would be much smaller. As written this way, for any fixed vocabulary, the length of the string is polynomial in the number of elements in the structure. And to keep that relation even for the special case of the empty vocabulary, we include the string of ones and write it in unary. Right? That's really the only purpose of this. And again, the point I emphasized before, which string you get depends on the choice of order, and therefore we write the string this way. Right? It is the representation of the structure A given a particular order on the elements of A. Now, think of this now as a decision problem, which is I give you a string and you have to decide whether the sentence phi is true in A or not. Well, this has a certain invariance property in the following sense, that I can define an equivalence relation on strings by saying two strings are equivalent if there is some structure and two different orders on it, such that W1 is the encoding of that structure under the first order and W2 is the encoding of the same structure under a different order. Right? This is an equivalence relation on strings. Now, this decision problem is invariant in this equivalence relation in the sense that if W1 is a yes instance of this decision problem, so is W2, and vice versa. Right? So, you cannot have two equivalent strings, one of which is a yes instance and the other is a no instance, simply because this is true whatever order you put on it, right? The formula phi does not have access to this order. We only use the order to encode the structure. Now, just a side remark that this equivalence relation, to deciding this equivalence relation, that is, I give you two strings and I ask you is their equivalent, is just what's known as the structure isomorphism problem. And we don't know how to do that efficiently. If we did, the whole picture would be rather different. So now let's get back to the question. The question was, how complicated is it? What is the complexity of deciding, given for a fixed formula phi, deciding whether a structure A satisfies it? The naive algorithm works recursively on the structure of the formula. When you have an atomic formula, RIT, right? We're talking about, we're assuming phi has no free variables. This would mean T is all constants. you just look up in the string to see whether this is true or not. The same thing for an atomic formula of the form inequality. Boolean connectives are easy. You do the usual recursion. If it's a conjunction, you check whether both parts are satisfied. Disjunction, negation, you kind of do the obvious thing. Whenever you have a quantification, you need a loop. That is, for every element of A, you take the formula psi, right, which is phi with the quantifier stripped away. Inductively, you're going to evaluate psi. But you replace all occurrences of the variable x with a new constant c, and you expand the structure by interpreting c by the element A. And you do this for each A, and if any one of these returns true, then you know that this existential formula, there exists x psi, is true in A. Okay, that's the obvious recursive algorithm. What can we say about its complexity? Essentially, you'll have a nested loop, one for each quantifier. So the running time is n being the number of elements in A, okay, raised to the power m, where m is the nesting depth of quantifiers in phi, and we'll multiply this by the length of the formula phi. That accounts for all the Boolean connectives and so on. Okay, so the time complexity is L times n to the m. N is the size of the structure. The space complexity, what space do you need? Well, essentially, you need, for every time you come across a quantifier, you need to create a pointer to the structure, and that pointer will point to an element of A and loop through all possibilities. So log n bits will suffice for this pointer. And if you have m nested quantifier, you might need m of these pointers simultaneously at a time. So the total space is order of m log n. Which means that if the formula phi is fixed, so L and m are constants, then this is polynomial time and logarithmic space. Okay. So in other words, for any fixed first order sentence, the collection of its models is decidable in logarithmic space and in polynomial time. Now, there are properties of finite structures which are easy to compute, well within logarithmic space, but which are not definable in first order logic. Examples include, there is no sentence of first order logic which is true in a structure if and only if the number of elements is even. This is known, and we'll even see a proof of this later on. There is no formula of first order logic that defines the transitive closure of a binary relation, right? So if you want a formula with two free variables x and y, for which the relation it defines when interpreted in a structure with a binary relation E is the transitive closure of E. And we can prove this can't be done. So this is a reason for going to, for example, second order logic. That means extending first order logic with second order quantifiers, relational quantifiers, such as, there exists an x phi where x is now a set or variable, which might be a set variable or ranging over binary relations, ternary relations, and so on. Here are some examples. I said that we can't express in first order logic that the number of elements is even. This is a formula of second order logic that expresses that the number of elements is even. I don't expect you to just look at it and read it, but it's actually not that difficult. What is it saying? It's saying there's a binary relation B and a unary relation S, so set S. Think of it this way. What we're really saying is B is a bijection, right? So for every element of x, there's an element of, for every x, there's a y which is related to it by B, and this says it is unique. Okay. And it is injective. So these two say that B is the graph of a bijection, and this says that B takes S to its complement. Okay, and the only way you can have a bijection from the domain of the structure to itself, which takes a set to its complement, is if the universe is even. And we existentially quantify the B and S, so we say if there exists such a B and an S. Now this will be true in a structure if and only if the size of the domain, the size of the universe of the structure, is even. Here's a formula of second order logic which defines the transitive closure of a relation E. Okay, so we want to say of a pair of structures that there is a path of a pair of elements, I should say, A and B, that there is a path from A to B in the binary relation E. How do we say this? Well, we say that if you pick any set S, which includes the element A, and which is closed under the relation E, which means that whenever X is an S, and there's an edge from X to Y, then Y is also an S. Together, these imply that B is an S. So if A is an S, and S is closed under the edge relation, then B is an S. And if this is true for every S, then it must be that B is actually in the connected component of A. The existence of a perfect matching in a graph is another property which is not definable in first order logic, but it's obtained easily as an adaptation of a formula I showed you earlier, which said that the relation M is a perfect matching. You existentially quantify that M, and now this is a formula which is true in a graph if and only if there exists a perfect matching. Okay, I've used this notation here for there exists a unique Y. It's easy to see how you can turn that into ordinary first order logic as I defined it. Here is a third example. Graph 3 colorability. This says this formula is true in a graph if and only if the graph is 3 colorable. Right? So think of it as saying there are 3 colors. Let's call them red, blue, and green. Every vertex in the graph has one of the 3 colors. For every vertex, it's not the case that it has 2 different colors. And whenever you have a pair of vertices which form an edge, then they don't both have the same color. So this says that there exists a valid 3 coloring of the graphs. Now, I give you this example because it's a bit different. Evenness and transitive closure and the existence of perfect matchings are all computable in polynomial time, but 3 colorability is not. This is an NP-complete problem. And so it's showing us that by adding this power of second order logic, we have increased our expressive power way beyond, because I did say every formula of first order logic defines a class of graphs which is decidable in logarithmic space and polynomial time. Now, the beginnings of the subject of descriptive complexity is really this lovely theorem due to Fagan, which says that a class of finite structures is definable by a sentence of existential second order logic, if and only if it's decidable by a non-deterministic machine running in polynomial time. Put in very short form, existential second order logic is the same thing as NP. Okay. Now, writing it as an equality is a bit strange because NP is a collection of decision problems on strings. Right? It's the way we usually define complexity. But ESO is a collection of sentences in a logic, and we're thinking of it as a collection of classes of structures. To actually relate them, you have to do this encoding of structures into strings. But the whole point is that what we've got then on the left is a way of talking about complexity, which is independent of the encoding into strings. We can really talk about complexity of abstract relational structures. A class of relational structures is an NP, if and only if it's decidable in existential second order logic. We'll take a closer look at Fagin's theorem in the second lecture. For now, I want to say that this theorem of Fagin's, proved in the 1970s, sort of inspired a line of work aimed at answering the question, well, we have this nice way of characterizing NP more abstractly, without reference to the coding of inputs into strings. Can we do something similar for polynomial time? Can we define a language like existential second order logic does for NP? Can we define a language in which we can only define polynomial time decidable properties of structures, and we can define all of them? In this form, the question was first posed by Chandra and Harrell in 1982, and it remains open, and it has driven a huge amount of research in the field of descriptive complexity. There is a sort of precise formulation. So Gurevich asked, in some sense, what would it mean for the conjecture, what would it mean to give a negative answer to the question? I mean, if we came up with a language, a logic, in which we could define all the polynomial properties, polynomial time decidable properties of finite structures and nothing else, that would be a positive answer. What would a negative answer consist of? How would we show the impossibility of such a logic? And he gave a very general abstract definition of a logic. We're not going to get into too much detail, but basically it's a recursively enumerable set of sentences with effectively a compiler which takes any sentence to a Turing machine and an explicit polynomial time bound, such that this pair, you run this machine with a clock which limits it to this bound, and that should accept a class of structures, which means it takes the strings encoding a class of structures, and it is invariant under this equivalence relation on strings that I defined. It's time for another pause.